Okay, so now we are going to use the stuff we did last time in terms of how we could distribute charge over a continuum and use that to calculate the resulting E fields that would happen over such a continuum. So, as a very quick review, whether you have Q or whether you have dQ does not matter. That little q, if I'm interested at what is going on at this point here, this q will create an E field at this point. Where dq, again, we are thinking of as just a little bit of charge. Because we are taking the actual amount of charge and smearing it out, over a rod, over a disk, over whatever. And so the dq element represents a little bit of charge with the intention that we will ultimately add them all up, which is just going to be an integral. So we know what the E field is going to be from this charge Q, or dQ rather. Instead of kq over r squared, I'm going to just write k dq over r squared, r hat. And since this entire expression has one of these dq's in it, I'm going to write dE instead of just E. It is, again, the E field that is created from this, but the D is, again, to imply that since this is a little bit of charge, I'm ultimately going to want to add things up, and I'm ultimately going to want to add up all these tiny contributions. And that's, again, essentially what we want to do with E net, which in the discrete case is the sum of the E fields. In this case, we're going to integrate over all of these little pieces. So I'm going to do this first problem essentially to death, then to do a second example kind of to death, and then the rest I will go quickly. The idea is to try to see if you can kind of conceptually understand kind of what's going on here. So let's do the problem of that you're at some point along the middle of a 1D rod of finite length, which has uniform charge density, lambda naught. And just to remind us, remember lambda naught is saying how the charge is distributed and is defined to be dq d x or y or z, depending on where the rod is. In this case, it's going to be along the x direction. So in this case, let's first draw a picture. And particularly, let's use the coordinate axes to our advantage. You can put down the coordinate axes wherever you want. But if we're going to have a point P that is along the middle of the rod, is offset, but is along the middle of the rod, then why not make that one of my axes? Particularly, let us make that the x equals 0 axis, or where I draw the y-axis. And then I'm going to put the rod along the x-axis. So we have our drawing that looks something like this. We have this point P, which looks like it's located at 0, y naught. And I'm going to use y naught in this case because the point P is going to be fixed. I'm curious what's going on at point P. And one of the challenges for these sorts of problems is that you have to identify kind of like what you're adding up. In this case, it's not too bad because we know that we have all these little bits of charge that are creating all these little E fields that we want to add up at P. P is not moving around. So I could write just 0, y, and we write 0, y naught, just to remind myself that y is a constant. It's just a number. And then, as I've drawn, I've put the rod along the x-axis with x equals 0 down the center. And I'm going to have the rod go from length minus L to plus L. I could do minus L over 2 to L over 2, but then I would have to deal with fractions in the expression. So let's just say the rod is of length 2L, and I go from negative L to L. So that's all well and good. So that would be kind of your first step. Draw a picture. The next thing to try to do is identify what are your little bit elements. And again, in this case, not too bad. Right, where we know the E field at the point P is the result of charges, particularly charges along the rod, where these charges, I'm not specifying where each individual charge is, but I'm giving a distribution through the charge density. So that means I should break up my rod into a bunch of DQ segments. A good thing then to do is to kind of in your drawing, draw or place, a representative DQ. Because when you do that, like I've drawn here, you can then also start to use it to define relevant variables. And again, what do we mean by that? Well, if I scroll back up, recall that this DQ is creating an E field, and that E field also depends on the distance between that DQ and the point P. So this R here, for example, is different for every little DQ. If you go back to this drawing, the DQ that I've drawn here, this is the vector R. Let's get rid of that P. Because that is the distance from that charge to the point. But I could use another color and say have this be another DQ on the rod, and that has a different value of R. So for the representative DQ, let me get rid of this one. For the representative DQ, we should be able to write down a general formula for the position that goes from that particular charge to the point. So if DQ is at the point, let's just say x comma 0, right? So we'll have this kind of go out to some x value. It could be a different x value for every little DQ, but I'm just leaving it as a general x in this case. So if DQ is at x comma 0, P is at 0 comma y naught, then R is points 2P from DQ, so it looks like it's going to be, we'll switch to column vectors, 0 y naught minus x 0, which then equals a vector that looks like it's negative x y naught. And of course, we should then ask, does this make sense? 0 comma y, that's a vector that points up. Then I'm subtracting from it x comma 0, so I'm subtracting from it the vector that points to the right. So then that flips the arrow, of course, and so then that looks like it equals an arrow that points left and up. And should I have expected an arrow that goes left and up to go from DQ to P? Yes, because that's the same as what I have drawn here. It goes left and up. So, all right, sanity check passed. That is the vector R. What else do we need? We don't actually ever need R, but we need its magnitude. So then that looks like it's going to be square root of negative x squared plus y naught squared, which is then just going to be square root of x squared plus y naught squared, which then allows me to define the unit vector as I take the original vector and I divide by that square root. So it looks like it's going to be negative x over x squared plus y naught squared, and then y naught over square root of x squared plus y naught squared. And that's my unit vector. And so at this point, I think we have defined all the relevant variables that we need, because we'll need an r, we'll need an r hat. We already have something for dq, and k is just a number. Okay, so we'll set that aside. We're going to need those. Maybe I'll even highlight them so we remember that they're there. Let's see, it's not really a formula or anything. I'll do it in green. So we have this that we're going to need, and then this that we're going to need. Now a good thing to do is to maybe consider, maybe we should have done this first actually, qualitatively, what do I expect? And by that I mean, does symmetry tell me anything about what to expect the answer to be? If I have a hunch for what the answer should be, then that can serve as a sanity check against myself. So again, I have this rod and this point P that's, that bisects this rod. It's right in the center. So if I think of, essentially just ask yourself, is there any symmetry in the problem? In this case, the fact that this point is along the line that divides the rod in two means that there's essentially mirror images on both sides. This dq is creating, I'll use red for E fields, creating an E field that points in that direction. But then this dq on the left is, and I'm choosing this dq to be the kind of mirror dq. So if this dq is kind of x to the right, this dq is x to the left. So then by symmetry, that dq is going to make an E field that points in this direction. And I expect it to be the same exact magnitude, but it's kind of mirrored over the x equals 0 plane. So in that case, I expect that, here, let me call this D1 and D2. I expect that when I add these things up, that is going to only have a vertical component by the symmetry. And you can kind of see that, just by looking at the drawing. I expect that there are x components, or if I were to break it up and, this vector has an x component here, and a y component, and then this vector has a y component and an x component. And looks like the x components will cancel, the y components will add together. But that's only for those two particular dq's. Do I expect that to happen in general? Well, yes, I do. Because again, I could take another dq, maybe a dq that's right on the edge, right near the edge. Right, so there's a dq over there. And it's going to create an E field that might point something like that. But then there's a mirror image over here that's dq, and it's going to have an E field that essentially is the mirror image of the other one. And again, the horizontal components will cancel, the vertical components will add. If I wanted to do yet one more, right, I could do essentially right before the center, right, these two dq's. And I think you see where this is going, right? Those are going to essentially be pointing in that direction. The x components cancel, the y components add. So by symmetry, right, they only have a vertical component by symmetry. And so therefore, we expect at the end of the day, the x component of the electric field to be 0, and the y component of the electric field to be non-zero. Particularly, it looks like it should be pointing up, based on the drawing that we've had there. So that's pretty nice. So that can serve, again, as a sanity check And again, like on a quiz or an exam, like if you can write me a 2-sentence argument for using symmetry, that is a perfectly valid answer. You do not have to, justify it with math unless I specifically ask you to. So learning to identify and use symmetry is very powerful. All right, so now we can write down with those expressions we had before. Let us try to actually write down something that we're going to be able to integrate. All right, because again, I want to compute E. So I can think of that as the sum of all these little dE's that are occurring from all the charges, right? And again, this equal sign is just just the concept. Integral is just a fancy adding machine. But then I'm going to replace this with our definition of that little dE. All right. Oops, r squared. And particularly now I can, so this is just, I guess, also concept, but we'll say definition. But now I'm going to bring over the work that we did on the previous page. And so to remind us that r squared in the denominator is going to be the square of this thing. So that's just going to get rid of the square root. And then the unit vector is going to be this thing, which notice it also has that kind of square root business in the denominator as well. So essentially we have a square root of this, because we're squaring it, and we have a third square root of this. That's going to be in the denominator of everything. So I'll write it out explicitly. So we have k dq, and then this is square root of x squared y naught squared, all squared. And then this is the vector negative x over square root business again, y naught. And now we could simplify this a bit. So then E is going to be, and I'm going to switch out of the column vectors and go back to brackets. So if I look at just the x component, again, we'll write this explicitly because why not? Right, essentially the denominator has this, because you have this component, and then that's being multiplied by the denominator of this, or I guess of the x component, which then is this. So you got this multiplied by this. So I have the square root of x squared plus y naught squared, essentially cubed, right? Because that's the same thing as the square root of x squared, y naught squared. But there's three of them now, right? Essentially you have the square root times the square root times the square root. But then that's nice, because then I can write it as x squared y naught squared to the 3/2, right, which is just what the square root is. So that looks like the x component is negative k x dq all over x squared plus y naught squared to the 3/2. And then the y component looks like it's k y naught dq, and then it's divided by, it also has a actually cube of the square root thingamajig. All right, so oops, I've lost the integral signs. Let's see, might as well just write it distributed for now. So I'm going to shift these over. So then I can write the integral and the integral. All right. Just like you remember from physics 1, the integral can distribute over the components of the vector. It's suddenly started downpouring. All right, so are we ready to do the integral? We're close, but if we look at this, I'm sorry, Forget to zoom in. But if I look at this, there's still some things to consider, because right now it says we're adding up over the charges. So I'm looking at where all the individual charges are, and I'm adding up this entire thing for each one. But for each one, the charges are located at slightly different x values, right? So I cannot treat this as a constant. So there's a relationship between where the charge is and kind of how much charge there is. Of course, this is where the charge density comes in. So knowing that dq dx is lambda naught, then says that dq is lambda naught dx. So again, I'm just rewriting, how much charge, but I'm rewriting it in terms of its position location. If this lambda were a function, then that would tell me kind of the local, amounts of charge, across the rod. Here we're doing it uniformly, so it's just a number times dx. So in this case, then that's great, because then x is something that is changing for every charge. Every charge is located at a slightly different x value. And this would allow us to write the integral in terms of x, which means then we can do the integral. Move that over. Not what it meant. There we go. Let's see. I'm just going to cheat. And then, all right, so then the dq gets replaced with lambda naught dx, lambda naught dx. And I can go even more now and say, like, since I'm integrating over x, because that's what's after the d, it's dx, I know that I'm going from negative L to L, negative L to L. And again, just so that it's super clear, these definite integrals means that x goes from negative L to x equals positive L. Where, and here's where I think writing the not was helpful. Why not? It's just a constant. Turns out when you do multidimensional integrals, like if you do an integral over x, you do just assume that if there are y's and z's, you just pretend they're constants, because you're only moving over x. So we could, we are treating y as if it's a constant. But I think the y, writing it as y naught helps us really remember that. K is a constant, lambda is a constant, everything else is a constant. Great. So now we have these two expressions, which really are not the prettiest. Let's see, how much room do I have? And then, actually, I'm going to move this to the next page, because there's a graph over there. I think it's worth having these on the same page. And that ultimately now our task boils down to that we need to evaluate these integrals. I'm going to get rid of the vector expression too. Right. This first one is the x component, so that first integral is ex. And then move everything else over a bit. Get rid of this silliness. And then this, then I put the comma back. Then this is just the y component. So our task ultimately now is that we need to evaluate these two integrals. But we also already thought through and said that we expect ex to be 0. We expect ey to be non-zero. We expect ex to be 0 and ey to be non-zero. Particularly, we expect it to be positive. So rather than, we could just charge forward. But again, if we can use symmetry to our advantage, then we can likely save ourselves a lot of work. So the goal here is, let's plot the integrams. this case. So essentially we are going to plot this negative k lambda naught x over x squared plus y naught squared, 3/2. And we're also going to plot k lambda naught y naught over x squared plus y naught squared to the 3/2. So again, just in case we need a refresher, the integrands are essentially the thing inside. I technically don't include the dx in this case as well. So really, what we're plotting here is, and if it makes sense to you that these are just the integrands, and what I am about to say doesn't make sense, that's fine. Ignore what I'm about to say then. Essentially what these are, if you go back up to the integral, if I were to take the derivative of ex with respect to x, it would be the integrand. Because again, the derivative cancels out the integral. So if I take the derivative of both sides, essentially the integral cancels out. And so then similarly, this is ey dx. But again, just think of them as the integrands. So let's do that here. So that is what this plot is. Move it over. Even make it bigger. So the blue line is e sub y, and the red dashed line, in case color doesn't come out for you, the dashed line is e sub x. So there are two properties that you might notice immediately. They do have a particular symmetry, and I assume you've used these terms before in a math course. Particularly, this one has even symmetry. And that just means I can mirror it across the x equals 0 axis, and it looks the same. And then this one, context clues might suggest, has odd symmetry. And odd symmetry is when you take your function, flip it across the x-axis, but then also flip it over the y-axis. So again, you can imagine I take this, and I flip it over the x-axis to become this, but then I flip it over the y-axis to become that. So where the even symmetry is, I take this, I flip it over the x-axis to become that. So why is that helpful? That is helpful because if I do think of the integral as the area under the curve, I can argue that the x component is indeed going to cancel, because the integral, for e sub x, that is the integral of, essentially this integrand. So it's going to be, all this area, which over here it's all negative, and over here it's all positive. But given that they are kind of mirror images of one another, that means, at this particular location, this little wedge of area is going to be exactly the same as its kind of mirror component, but that one's going to be positive. So when I add these two together, they're going to be 0. Similarly, when I add the rectangle, right here and right here, those are going to cancel. The rectangle from right here and right here, those are going to cancel. So in this case, just geometrically, just visually, I can already tell the integral is going to be 0. Where then the y component, this rectangle, which is the mirror of this rectangle, they're identical, but they're both positive, so they're going to add together. However, you can think of this, and you can actually change the limits of integration. So if the integral is the area under this entire curve, right, that's what we want to evaluate. But since this part here is exactly the same as this part here, I could get the same exact answer if I just took this part and multiplied it by 2. So just by the, I'm going to make this smaller again. Sorry, even odd. So in this case, then, again, arguing by the odd symmetry, we do expect the integral of, well, we do. We expect e sub x, which is then the integral of negative kx lambda naught blah blah blah, dx from negative L to be 0. And then because of the even symmetry, we're not going to be able to avoid having to do an integral, but again, the integral from negative L to L of k lambda naught y over blah 3/2 dx, right? That is the same thing as, I'll write the same exact integral k lambda naught y over blah to 3/2 dx, but I'm going to multiply by 2, and then I only have to go from 0 to L. Because again, I could figure out instead the area under laser pointer, the area under this part only, and that's just going to be, then this part is just going to be the same. So sometimes this is helpful because I can take an integral where I have to go from negative L to L, and I can turn it into an integral where I just have to go from 0 to 2L. And I know that, or I know the chances that my life simplifies when I get, or the chance that my life will simplify because I get to plug in 0 in this case is probably a lot higher than if I were plugging negative L's and L's. Of course, you could do either integral. You should get the same answer. You must get the same answer. All right, anyway. So again, there's another symmetry argument, right? Just by knowing that the function is even or odd, right, allowed me to say something about the evaluation of the integral. Now let's actually brute force do these things. So the x component, which is the integral of negative k lambda naught, what was it? That one had the x? Yeah, that one had the x. X dx all over, I'm going to drop the naught on the y, all over that from negative L to L. People in Calc 1, don't worry, this is an integral you do not know how to do yet. People who took Calc 2, say it with me. Trig substitutions, of course, you can do those trig substitutions, and the antiderivative ends up becoming k lambda naught over the square root of x squared plus y naught squared, and then that's evaluated from L to negative L. And lo and behold, right, the lambda naught is a constant, so it looks like it's just k lambda naught. Then I'll plug in L for x, so L squared plus y squared, and I subtract what I get when I plug in negative L. So then I still get k lambda naught on top. But then notice it's going to be negative x squared, or negative L squared. I'll just write it out explicitly. But negative L squared is just the same thing as L squared. So notice that this and this are exactly the same. And I'm subtracting them, so I get 0. As we anticipated. E sub y, we said is going to be actually twice from 0 to L, k lambda naught y over x squared plus y squared to the 3/2 dx. And then you do that fun stuff again, and it ends up becoming k lambda naught times x all over the square root of x squared plus y squared. And that's, oh, I dropped it, my 2. Yes, okay, and then that goes from 0 to L. And again, here's where it's great, because I can first plug in, L to for x, so I have 2k lambda naught L over, I lost a unit. The units don't make sense. Oh, there's a y in the denominator, sorry. So it's 2k lambda naught x divided by y, then also in the denominator is the square root. So then this becomes 2k lambda naught L y, then I plug in L for the x, so that becomes L squared plus y squared. And then I get to plug in 0 anywhere I see an x. And there's an x in the numerator. How nice. So then it seems like the answer at the end of the day is 2k lambda naught L all over y square root of L squared plus y squared. Oof. Not the prettiest expression, but if we look at it, indeed it is non-zero, and indeed if I look at all these quantities are positive quantities, so at the end of the day, looks like I have figured out the E field of the wire has no x component, and then is 2k lambda naught L divided by y all over the square root of x squared plus y squared. Oops, L squared plus y squared. That's all in the square root. That's the y component. And that is the E field at the point P, 0, y. So that was a lot. That took some work. But I would say we're still not done. All right, you should still make sure that this thing makes sense. But I will highlight it. Right, because you also have to remember, like, when is this formula applicable? This requires us to be kind of in the middle of the rod. So if you were if this is the rod and we're curious about this point here, you better not use this formula, because this formula was derived assuming that you're at some point, along the line that divides the rod in half. So, what other things can we do? Well, you can check units, right? I'll let you just read through that on your own. The units make sense, and we should see kind of like what sort of assessment sanity checks can we do. So let me redraw the picture. Here's our point P. Here is our rod. And we have figured out that the E field points directly away from the rod, like so. So looking at extremes, so we're looking at limits, can kind of help you assess, whether or not these things make sense, and may also reveal something new. So, like, for example, if L goes to 0, then, actually, let me copy the result. Let's copy this. Put what I wanted. Erase highlighter. Okay, so and this is E sub y. So then if L goes to 0, well, then there's no rod. And notice that there's an L in the numerator, so that EY then goes to 0. Okay, that makes sense. If the rod vanishes, the E field better vanish. Now, what about if y goes to infinity? So in this case, you're moving that point P farther and farther away from the rod, so that now the rod, this finite length rod, is this tiny little blip on the horizon. Right? You can imagine if you're looking towards the horizon, and you're far away. then this rod, which might have started that big, but then as it gets farther away, like things that are off on the horizon, kind of looks like it's farther and farther away. Maybe I'll do it as a series. So, particularly if you look at when it's really far away, it kind of looks like a point along the horizon. So I know the E field for a point. I know the E field for a point charge should be kq over, in this case, y squared. Does this more complicated formula actually become that? Well, let's take a look. So the total charge on the rod, right? So again, that's q, which then it just means I want to do the integral dq. But then by the charge density, that's lambda naught dx from negative L to L, because I'm integrating over the rod. So then it looks like that is 2L lambda naught. I'll let you fill in the blanks. So the total charge on the rod is 2L times lambda naught. And if I look at E sub y, notice that there's a k, but then there's a 2L and a lambda naught in the numerator. And then it's divided by y and this square root business. So E sub y, I could have written this as k kind of q total over y L squared over the square root of L squared plus y squared. Okay, that still doesn't quite look like kq over y squared. But now let's consider the limit that y is really, really big. Y is going to infinity. I could also assume that kind of y is much, much greater than L. So in that case, then, the square root of L squared plus y squared, right, that's essentially just then square root of y squared. You could think of it like, sometimes I like to think of it in terms of money. Like, if you had, $1 trillion and I gave you 1 penny, your total worth is essentially still $1 trillion. That penny has not really changed your total wealth. So just like if y is, if this is 10 to the 30, and then you square it, and then y is only a meter, that 1 meter essentially gets swamped out over the y squared. So in that case, that becomes essentially the square root of y squared, which is the same as y. And then notice that then E sub y kind of goes to k q total over y, and then that square root business just became y. So indeed, looks like k q total over y squared. Kind of what you would expect, of a point charge. Now, again, so there's no confusion. You might be saying, but this is not a point charge. It's a rod. And you're exactly right. But what we're talking about here is that we're considering looking at the rod really, really far away. What is the electric field from this rod? Absurdly far away from the rod. And just like how things off on the horizon start to look like a point, this rod essentially starts to look closer and closer to a point. And we're seeing now that in the limit that it looks like a point along the horizon. Indeed, the E field essentially is approximately what you would expect for a point along the horizon. Again, these are just kind of sanity checks, but kind of are also good because it's, this time it's the first time you're thinking and hearing about these things. So we're also able to reinforce these ideas. Now, the other two limits are actually kind of subtle. When y goes to 0, when y goes to 0, you might think by symmetry the E field should be 0, because if I'm exactly in the middle of the rod, then you might imagine that all the stuff on the left is going to create an E field going this way. Then all this stuff on the right is going to create an E field going this way. But then that is missing that one infinitesimal charge that you happen to be sitting on top of. So it's actually a bit subtle to deal with that, which means we are not going to. But then we could consider we could consider what the rod looks like as y goes to 0. So we're not going to let it be exactly 0, especially because then we're dividing by 0, and that's frowned upon. But I'm going to let y just be absurdly small. Equivalently, right? So, I could, it's kind of equivalently, let y be absurdly small compared to, not r, wrong problem, L, which means, I'm just, I'm essentially have my nose up against the wire. Or that's essentially the same thing as letting L go to infinity. And the idea might be that, if you were looking off and there's a kind of a, suppose we're in China, and we're visiting the Great Wall of China. We're viewing it from a distance. From a distance, it looks like this kind of like small thing, because we're very far away from it. But as we walk closer and closer and closer to it and essentially get right up next to it, the wall suddenly looks a lot bigger, right? If we literally are, our nose is about to touch the wall, we're so close. Essentially, the wall takes up our entire field of view. So it looks essentially like it expands forever in all directions. So essentially, we could think of this as either letting y be absurdly small or letting L get absurdly big, right? You have a very, very long wire. Well, in that case, E sub y, and let's just do it in the limit that L gets enormous. So in the limit that L gets enormous, we have a similar sort of thing like what we have, we have a similar sort of thing what we have here, but for L instead of y. So in this case, then, E sub y, which is k lambda naught L over y. And then there's the square root of L squared plus y squared. But I'm going to let L get enormous. The numerator has an L. Okay, so the numerator is getting big. But then the square root thing is also getting enormous. So then that's going to be k lambda naught. Just keep the numerator as is. But then the denominator is just going to become L. Because again, it's going to be L squared plus y squared is approximately just square root of L squared, which is L. The y is so small, it's inconsequential relative to L. So in this case, then it looks like, what does this become? So then it looks like it's k lambda naught. Looks like the L's cancel. Interesting. Which also kind of makes sense. If L is going to infinity, then the value of L should disappear, right? Because we're essentially letting it be as arbitrarily big as we want. So it looks like then this is k lambda naught over y. I've lost a 2 somewhere. Okay, hold on. Pause. Oh, right, because the 2, if I write it as q total, it absorbs the 2. But here, I did not write it like that, so there's still a 2 flying around. Sorry about that. So in this case, move this over. This is the expression for the infinite wire. So the infinite wire has an E field that is still 0 in the x direction. There's 2k lambda naught over y in the y direction. And again, we got to this expression essentially by thinking that either y is so small that the wire expands our field of view. Again, just try standing next to put your nose up against a wall, right, and see how big the wall looks. Or we just let L get really, really big. So this is a useful approximation for when you're calculating E-fields. Because of course there's no such thing as an infinite wire. But maybe if we understood kind of when this was applicable, maybe this actually is applicable, and is a very good approximation for most cases. So, and I would consider this, I guess, optional. So, if you want to skip ahead in the timestamps, you can to the wire, but I'll just go quick. Right, the real rods are of course not infinitely long, but oops, I did not switch to that notation yet. It still wants to only do highlighters. Why? But it might be that the infinite rod is a good approximation for a lot of cases. When is the rod approximately infinite in terms of the E field that it contributes? Because again, if you go back to the E field, like the one we derived, this thing here, you could plug in some values, right? Plug in a value for Y, plug in some values for L and lambda and K, and then just keep plugging in bigger and bigger values for L and see what happens to this thing. Another way to think about it is that you could essentially take a ratio and non-dimensionalize things. So you want to compare the electric field from the kind of finite wire versus the electric field for the infinite wire. And so what I'll do instead is I will consider kind of the finite wire. I'm going to divide that by the value for the infinite wire and see what expression I come up with. So for the finite wire, we had 2k lambda naught L over Y, and there was that square root business. And then for the infinite wire, we had 2k lambda naught all over Y. And here's where this is great, because look at all this cancellations going on, right? This k, this messy k, the lambda naught. We don't even need to know the value of lambda naught. To the 1 over Y is all gone. And ratios really are the key to life. And so this looks like it becomes L over L squared plus Y squared. And this is a function that, now again, we're thinking of this in terms of like, we're letting L get bigger and bigger and bigger. So it might be nice, we know that this left-hand side is non-dimensionless, or is dimensionless rather, because it's an E field divided by an E field. So we do expect this to be dimensionless, which it is, because this says units of length, and then this says units of length, because it's length squared, square root. So it's sometimes helpful to write things in terms of some dimensionless parameter. So essentially what I'm going to do is I'm going to divide the top and the bottom by Y. So that's going to be L over Y, and then the square root of L squared over Y squared divided by Y. The top is just going to stay L over Y. But then what I'm going to do here is I'm going to take the 1 over Y back into the square root. So, if the square root of x squared is just x, then if I want to move the x back in, I have to remember to square it. So then this is the same thing as L squared plus Y squared. And then that 1 over Y, if I bring it back into the square root, right, that becomes Y squared. And it's all in the square root. So then this looks like it's L over Y, all divided by the square root of 1 plus, then there's also L over Y, but it's being squared at the end of the day. It's getting the Y squareds cancel, and then you have L squared divided by Y squared, which then I just made L over Y all squared. So I could write this, say, as, maybe eta divided by 1 plus eta squared, where eta is L over y, which is a dimensionless number. This is dimensionless. And it's nice because essentially it gives us a way of quantifying the length of the rod, right? Rather than having to plug in 3 meters or 10 meters, I could say is the length of the rod 2 times the length of y, 10 times the length of y, a half the length of y, because that's going to be what quantifies whether or not I'm close or far away from the rod, or how big the rod is, rather. This is y, right? This is kind of L is much bigger than y, versus this is the rod and this is y. Then, in this case, L and y are kind of comparable. I would not call that an infinite rod. So anyway, you could make this plot where I'm plotting things in terms of this eta factor I've created, L over y. So essentially this is a way of saying the rod length as a factor of y. So when eta equals 2, well, that means that L over y equals 2, or that means that L is 2 times y. So this is when the rod is twice the length of y. This is when it's 5 times the length of y. So as you go this way, the rod is getting longer and longer and longer. But I don't have to worry about units or anything like that. And then this is the ratio of the Efields. So notice it starts 0, and then it climbs up and eventually starts to look like it's asymptoting to 1, is what you would expect. When it asymptotes to 1, that means that EY of a finite rod over EY of the infinite rod, if that's approximately 1, then that means that the finite rod is well approximated by the infinite rod. And the thing to note is that you actually don't have to go that far. When you're only 5 times, when the rod is only 5 times the length of y, then this ratio is already 98%, which means this infinite rod case, this 2k lambda naught over y, is essentially the electric field to within a 98% accuracy, as long as the rod length is at least 5 times the value of y. And of course, as it gets bigger, this asymptotes closer and closer to 1. Right, so that suggests that you actually don't need to make the rod that long for this infinite rod approximation to be a good one. So we'll just use the infinite rod approximation. Another thing that's nice about the dimensionless way that we did this is that this stuff here, right, that eta as a L as a factor of y. And I'm saying that when it's equal to 5, then it's 98% the infinite value. So that is true regardless of the length scale. So if y is 1 meter and L is 5 meters, this is true. If y is 10 micrometers and L is 50 micrometers, this is true. If y is 6 gigameters and then L is 30 gigameters, this is true, because all of those are L is a factor of 5 bigger than y. And that is what this axis is telling you. So usually very helpful if you can non-dimensionalize things. All right. How long did that take me? Oh my god, that one problem took me an hour. Oh geez. I don't really want to. I don't think I have the energy, or you have the energy to listen to more problems. Okay, so we're gonna have to break this one up. But so I would focus on kind of the steps, kind of going through, and then I'll work in this ring. Will be kind of a problem that we work on in class. And then once we have those, we can just look at the we can look at the book and use the results of a disk. So essentially where we're going is the next problem to do is a ring of charge. So I take my wire and I bend it into a ring. And then I consider some point kind of off the center of the ring, right? So some point here. That's kind of in the symmetric center of the ring. From that, we're going to then do the disk, which you can think of the disk as just a bunch of rings, but each ring has a slightly different radius. And then we're going to let this disk get bigger and bigger and bigger. So it essentially then becomes an infinite sheet. Okay, that stretches off in all directions. And again, that's an approximation, but we can do the same sort of analysis and see that it's actually a decent approximation. And where this infinite sheet plays an important role is when you have two sheets next to one another. So you have kind of infinite sheet here, infinite sheet here, and one's positive and one's negative. So this is called a parallel plate capacitor. Your smartphone and your laptops have bunches of these, in them. Usually they're kind of the two sheets that are kind of rolled up into a coil, into a cylinder. But we'll have to, this is something we're going to see a lot the rest of the semester, so we'll have to study that one in detail. All right, so I guess here's all the answers, but the goal in class is we can work through together the loop, and then from there we can just kind of argue what the 2D one should be and use that to do the capacitor. So I think that'll be a good strategy rather than me doing yet another derivation. But you might try it on your own. I mean, it's in the book as well, where you could see kind of, could you follow these steps and like sketch it out for yourself? Maybe not necessarily do the integrals, but just kind of sketch out the steps. All right, I forgot to say something about the infinite wire, or the finite wire as well. But let's look at the infinite wire. So, in the case of the infinite wire, it just goes off in the x direction forever, which you might think is that's an infinite amount of charge. Again, infinite rods don't exist, but we saw that this is a good approximation. And if this distance was y, we wrote it as E was 2k lambda naught. Let's see, for the infinite rod over y, correct? Infinite wire 2k lambda naught, yeah. And then this points in the y direction, we said. Now, of course, not all wires need to be along the x-axis, and the point need not to be, along the y-axis. So, right, so we might try to think of how we could generalize this. So, what do we notice? The geometry of the problem, notice that the wire is kind of going off to the left and to the right. And then there's only one distance in the answer. The only distance is this y. The only distance that really matters, and we know the E field has to depend on distance. Or we expect that it should. Just thinking of Coulomb's law. And the length that seems to matter is this y. And really it's because this value here, and notice that it's essentially what I call the normal distance. Again, that's not me making a statement about the wire, or the distance. But again, normal being a fancy word for perpendicular. And that it's essentially the one distance that's not ambiguous. If I wanted to think about the distance to this point P, there's an infinite number of distances. Like, is it this distance, or is it that distance, or is it that distance, or this distance, or this distance? And this y, essentially, this distance here, which is, and that's also the minimum of all those distances, is kind of the one non-ambiguous distance. And it only is depending on the kind of perpendicular distance from the wire. Because again, it's not, this distance where there's a kind of parallel component and a perpendicular component. But this distance here is purely perpendicular to the wire. And it matches the direction of Efield. So we could think of, like, what if I had, you know, some general setup where maybe the wire is kind of oriented like that. And then I have some point P here. Now, if it's an infinite wire, then we don't have to worry about whether or not P is in the center or not, because if the wire is infinite, it of course is in the center, right? Actually, every point is in the center, right? If the wire truly is infinite, because you could find just as many points to the left, you know, as to the right. And so then the distance here that matters is that we find this distance that is perpendicular to the wire. It's not quite a right angle, but go with me here. So your book unfortunately calls this R, which I feel like we already have too many things that are called R. So I will match the book with a slight change, and I'm going to write, I'm going to not make it as thick. I'm going to write this as R, and I'm going to put a little perpendicular subscript. Just to make it clear that it is kind of the vector that is perpendicular to the wire and points to P. So R perp points to P from the wire, but we need to make it non-ambiguous such that R perp makes a 90-degree angle with the wire. And again, that's just saying that it's perpendicular to the wire. And that happens to be the direction that the Efield points as well. So essentially what we're going to do is, the general form is I can write E as, well, let me not do it as a vector, well, as components. That we're going to do 2 lambda naught K, but then I'm going to write this as just R perp, because it's just whatever that distance is between the wire and the point P. And then this is in that direction, right? It's in the direction that kind of points away, you know, from the wire. All right. So that might be the general way we write this, right? And that you just have to remember kind of what these symbols stand for, right? That this is the perpendicular distance from the wire, and this points away from the wire. We'll see this again when we do the infinite sheet, where essentially, you know, the electric field is going to point away from the sheet. So it's this kind of perpendicular distance that might play a role. Turns out it does not, but that at least helps us get the direction. Okay. Sorry, I forgot to say that earlier.